Hi everyone, this is Dr. Mani. In the previous lecture, we discussed the basics of finite element analysis, and in this session, we're going to see some introduction about finite element analysis. And in engineering analysis, we have a number of types of analysis. For example, like structural analysis, vibrational analysis, fatigue analysis, heat transfer analysis. If we take structural analysis, it consists of linear and nonlinear models. In both the linear and nonlinear elastic materials will elastically return to an unloaded state after loading, that is without getting permanent deformations. But the relationship between stress and strain is different in both the cases. If we take in a nonlinear static analysis, the model stiffness matrix is constant and the solving process is relatively simple compared to a nonlinear analysis on the same model. Therefore, for the first estimate, the linear static analysis is a primary stage to perform a full nonlinear analysis. If we take nonlinear models, it consists of stressing the material past its elastic capabilities. The stresses in the material then vary with the amount of deformation. These nonlinear effects can originate from geometrical nonlinearities, that is, large deformations, material nonlinearities, that is, elastoplastic material, and the contact analysis. These effects result in a stiffness matrix which is not constant during the loading application. This is opposed to the linear static analysis where the stiffness matrix remain constant. Then we have heat transfer analysis. It consists of steady state or transit transfer. Steady state transfer refers to a constant thermal properties in the material that yield linear heat diffusion and also helps to model the conductivity or thermal fluid dynamics of the material or structure. Then in vibration analysis, it is used to test a material against random vibrations, shock, and impact. Each of these incidences may act on the natural vibrational frequency of the material, which in turn may cause resonance and subsequent failure. Then, if you take fatigue analysis, this analysis helps designers to predict the life of a material or a structure by showing the effects of cyclic loading on the specimen. And this analysis can show the areas where crack propagation is most likely to occur, and failure due to fatigue may also show the damage tolerance of the material. Then we'll see process of the finite element analysis. Here we have three stages. Starts from physical problem, then a mathematical model, and finally a numerical model. The physical problem involves in an actual structure or a structural component subjected to various loads. Then the idealization of the physical problem to a mathematical model requires certain assumptions like geometry, material data, loading, and boundary conditions that together lead to differential equations governing the mathematical model. This model completely determines the insight into the actual physical problem that we can obtain by the analysis. The selection of mathematical model must depend on the response to be predicted. To solve this mathematical model, we are using numerical model like finite element analysis method. Since the FEA solution technique or FEA model or FEA analysis is a numerical procedure, it is necessary to assess the solution accuracy. If we are not getting the accurate solution, we may go for finite measures until sufficient accuracy is reached. We cannot predict the response of the physical problem exactly because it is impossible to reproduce, even in the most refined mathematical model, all the information that is present in nature and therefore contained in the physical problem. Once the mathematical model has been solved by numerical model accurately and the results have been interpreted, we may go for next refined mathematical model in order to increase our insight into the response of the physical problem. Whatever mathematical model we are selecting for the physical problem, it should be effective to get sufficient accuracy and at least a cost, and it should be reliable. And we'll discuss what is finite element analysis in general. This determination of the solution for a complicated problem by replacing it by a simpler one. This is the general concept about finite element analysis, what it says actually. Then geometrical complex domain represented as a collection of smaller manageable domains, and solution to these geometrical similar domains is easier. Replacing the original complex geometry as an assemblage of smaller simple geometry will result in only an approximate solution, useful for problems with complicated geometries, loadings, and metal properties where analytical solutions cannot be obtained. So, only in these areas, FEA is most useful. And like this way, we can define finite element method. It is a numerical method for solving system of governing equations over the domain of a continuous physical system, which is discretized into simple geometric shapes called finite element. And here we have shown both the categories, what is continuous system and what is discrete system. And like this also we can define FEM. It is a computer aided mathematical technique that is used to obtain an approximate numerical solution to the fundamental differential and or integral equations that predict the response of the physical system to an external effects. External effects or external influences defined like this. When a bar is subjected to an axial pull P, it elongates. Here the external influence is axial pull. When a metallic rod is heated, its temperature rises. Here the temperature or whatever heat we are applying to the metallic rod, it is the external influences. When a beam is subjected to an external harmonic excitation, it gets vibrates. And in FEA, we have basic steps. That's number of steps to solve any kind of FEA problems. And we have different phases of FEA. And if you look at basic steps, we have first stage or first step is discretization. The domain is represented as a collection of finite number of subdomains. Domain is a basic structure and that will be divided into number of subdomains, and each subdomain is called an element. The collection of elements is called mesh. The elements are connected to each other at points called nodes. And this is the first very basic step. What is discretization? Then the next stage we have to select selection of approximate of functions. That is shape function for element whatever we define in the first stage. The next stage we have to form the element matrix, then element loading matrix, then we have to assemble all the matrices, all the element matrices, and we have to get one simple assembly matrix by applying all the loading cases. Then we have to implement the boundary condition. Then finally we have to calculate the unknown nodal displacement, stresses and strains. And these are the stages we have or steps we have in FEA. And these are the phases involved in finite element analysis: pre-processing, solution and post-processing. In the pre-processing stage, a finite element mesh is developed to divide the given domain or the geometry into subdomains for mathematical analysis, and the material properties are applied and also the boundary conditions. In the second phase, that is solution phase, the governing matrix equations are derived and the solution for the primary quantities is generated. And the third phase, called post-processing phase, checking the validity of the solution generated, examination of the values of primary quantities such as displacements, stresses and errors involved in is carried out. And we have number of engineering analysis to solve any kind of engineering problems. The first one is experimental analysis. So this deals about prototype. So to solve any kind of analysis, we have to make some prototype models, and by using those prototype models, we have to solve the problem. And the next analysis is analytical analysis. Here we can make simple geometries and we can solve the given problem. And the third one is numerical or approximation solution techniques. And in this technique, we have number of methods like weighted residual method, finite difference method, Rayleigh-Ritz method, finite element method. Out of this, finite element method is most widely used method for all the types of analysis. Thank you.